Hi everyone, my name is Lasah Ming. My metric number is A20MJ1027.
Hi, Assalamualaikum. Okay, my name is Amanina Binti Azmir. My matrix number is A20MJ0081.
Hi, I'm Alfiana Nabila and my matrix number is A20MJ0154.
Assalamualaikum and hi. My name is Rabiahtul Adawiyah Binti Othman and my matric number is A20MJ0099.
Hi, konnichiwa. My name is Haida Azwa Binti Mohmad, number matric A20MJ0077.
Today I'm going to talk about the introduction. The topic that will be covered in this report is an example of how to solve the application of second-order differential equation. The question that we choose is question number 1 regarding a vibrating string without damping. This question is related to mechanical vibration, specifically free undamped vibration. Vibration can adapt to various situations, so this makes vibration can occur in almost any branch of engineering. One example of the application of a mechanical vibration is a mass hanging on a spring. 4 forces that is assumed to act upon the object are gravity, spring, damping, and external force. The first one is gravity. The force due to gravity will always act upon the object of the course. Next is spring. Hooke's law is assumed to govern the force that the spring exerts on the object. Hooke's law explains that the force exerted by a spring will be the spring constant. The third is damping, or FD. The damping force will always act to counter the current motion of the object and so will act to damp out any motion in the object. The last one is the external force, or FT. Other strengths beside the before are included here.
The problem description in this question are: a second-order ODE is an ODE that contains one or more derivatives of the unknown function. The most common form of an second-order ODE is for each of the equation we can write that so-called characteristic auxiliary equation. Second, the general solution of the homogeneous differential equation depends on the roots of the characteristic quadratic equation, which is the solution of this homogeneous differential equation is z equal to a cos ut plus b sin ut. Third, for the question A, we must know the general formula for complex solution. This is an expression of the acceleration of an object that performs linear simple harmonic motion. The negative sign indicates that the acceleration is in the direction of the average position or opposite to the direction of displacement. Fourth, for question B, we just substitute given frequency into the equation A and find the beta to get the new value of f, which is frequency.
Methodology 1. Overview of the method used to solve the case. For this question, we already analyzed that this question is in the second order of ODE. The question given that my prime plus ky equal to 0 is an example of second order of ODE. Why the question is in the second order? This is because the highest order of unknown y is 2, which is also familiar as d squared y over dx squared. For question A, to find the equation of the motion for the system, we need to identify the root of the equation by substitute u squared into k over m and d squared into d squared y over dx squared. Then we will get the root, which is complex number, thus the equation will become z equal to a cos 5t plus b sin 5t. Next, we need to differentiate the equation that we get previously. Then we can find the value of a and b by using the all values given in the question, such as m, k, y, y prime. At the end, we will get the complete equation, which is z equal to 0.3 cos 5t minus 0.02 sin 5t. For question B, we need to find out the frequency of the oscillation for the spring system of part A. We can solve this question by using the value given in the question, which is f equal to beta over 2 pi. We need to substitute the value of f into t, which will become y bracket f equal to 0.3 cos 5 beta over 2 pi minus 0.02 sin 5 beta over 2 pi. Then we will differentiate the equation 2 times until we get the equation of d squared y over dx squared. After that, we can substitute the equation into the original equation, which is m y prime prime plus ky equal to 0. Then we will get the value of beta, which is beta equal to 4.7929. Lastly, we will substitute the value of b into f. Thus, we will get the value of frequency, which is 0.76 Hz. So, this is the solution that we use to solve question A. And this is the solution we use to solve question B.
Hi, my name is Lasah. Now coming to my part, which is the result and discussion. First of all, thank you for the previous presenter. Now, my name is Lasah and coming to my part of my presentation is the result and discussion. Part is result. For the first step, we need to analyze the questions. So we already done with the analysis. This question is about second higher order of ODE. And then the result for part A, after you already seen the manual calculation that presented by my previous presenter, the result is the final answer for part A is z equals to 0.3 cos 5t minus 0.02 sin 5t. For part B, for the result part B, the final answer will be, because the question asking the value of frequency, so we get for the value frequency, which is 0.76 Hz. So we coming for the fourth, which is the similarity. Both of the question that needed using differentiation and substitute method to solve the question after knowing the highest order, which is the first equation give us the y, we have second highest order of unknown. Coming to the second part, which is the discussion. So we know that and we discuss and prove that the equations and the question is about the second higher order. And the second thing is understanding. We can more understanding the type of second order of ODE questions. And then the last thing is teamwork. We can help each other to understand more about this topic and the way how to solve these questions.
To sum up everything that has been stated in this assignment, we were able to solve question 1 by using application of second order differential equation. To be specified, the question is a homogeneous nonlinear ordinary differential equation. As I stated in introduction, the derivative of the first and second order differential equation varies. It is differed in which the highest derivative in a first order differential equation is a y prime, which is dy dx, whereas the highest derivative in second order differential equation is y double prime, which is d square y over dx square. An ODE with one or more derivative of the unknown function is called a second order ODE. Y double prime plus p bracket t y prime plus q bracket t y equal to 0 is the most common form of second order ODE, where p and q are time functions that are generally unknown functions. By referring to the question, it states that there is a vibrating string without damping. Hence, we can assume that this question is exit as in vacuum chamber that might have a spring mass system in there. The mass would keep moving up and down endlessly if there was no air resistance. The term undamped refers to the absence of energy losses as a result of movement, which, whether intentionally by adding dampers or unintentional through drag or friction. Without any extra applied pressure, an undamped system will vibrate indefinitely.